Okay, diving deeper into this business of this wire sitting on the mesh. Okay, on the wire frame, not mesh, wire frame. So this is my wire frame, it's conducting, right? And this is my conducting bar. And this is sitting in a magnetic field pointing into the board. The magnetic field is everywhere and it's uniform. Okay. And you pull this bar, so you have a circuit here formed because this is in contact here and there. It means in contact, and you slide this in this direction at speed v, and I mentioned in the previous video that there is going to be an induced current, and the current is going to flow in such a way so that it opposes the change in the magnetic flux in this part of the loop, in this loop, this part of the figure. So this is I induced flowing this way, right? And we would like to see, I mean, I mentioned that there is magnetic resistance and there's force from the part either in the notes or in the videos on the interaction between moving charges and magnetic fields. We know now that there is the force on the, you have a main magnetic field. We're going to call it B external just to make sure that this is not the induced magnetic field, and you have now B induced, because of the current. The B induced is going to be here, opposing the change in the flux, right? Because this loop is expanding, so this is B induced here. So what we have now is a magnetic field that created a current I induced, and this magnetic field is going to interact with the current, right? Think of the force that the magnetic field will exert on that current, and F is equal to what? I L cross B. Okay, so L is the length L here, right? And I is the current flowing. This is now I induced in this case. Okay, we said that I induced from the previous discussion is equal to magnitude. I was equal to B L V over R. Let's think about the force that we have to apply. So which way, how does this work? Which way is the force? Well, I mean, I is this way. The L points in the direction of the current, so L is this way. B, I induces up, B induces into the board, so do the cross product. L cross B. The index points along the direction, the thumb points along the direction of the first vector in the product, which is L. B is along the index, and the middle finger gives you the cross product, which in this case is the force. So I is that way, B is that way, the force is that way. The force, the magnetic force, F magnetic, okay, FB is going to point that way. So just by virtue of this, the fact that this guy is moving at a constant speed, we have a force opposing this motion. So for us to be able to continue this moving at a constant speed, we need to exert a force in this direction, F mechanical if you want, okay? And that has to be equal to FB. Well, what is the magnitude of this force? That's equal to, if this is moving at a constant speed, this is equal to that. So F mechanical is equal to F magnetic, and this is F magnetic in this case, and this is equal to I induced is, L cross B is what? L is this way, B is that way, so that's the force, but the magnitude is LB sine theta. L is this way, B is that way, so the angle is 90, and that becomes in magnitude ILB, and that becomes BLV over R multiplied by LB, and that gives me BL squared V over R. Okay. So B squared L squared V over R. Okay, so this is the force, the magnetic force that you have to, okay, or the mechanical force that you have to apply has to be equal to this magnetic force. And now the question is, how much power, okay guys, how much power is, I mean, let's think of this. You have current flowing in a loop which right now has resistance R, okay? This part of the loop, or this part of the diagram, this loop has resistance R, and you end up with this much force that you have to push this thing with, okay? So let's think of two things now, okay? What is the, if this is just purely a resistive circuit, how much energy is lost to heat? What is power? P is equal to I R, I squared R, right? So the power is equal to I squared R, and that's going to give me, if we, you know, this is P lost in heat or resistance or whatever. What is that equal to? I is equal to V LV, right? LV over R, right? That's squared multiplied by R, right? And that's going to give me B squared L squared V squared over R, okay? Okay, fine. What is this power coming from? I mean, energy. You think of generating, you know, a generator. I mean, how much power, how many homes can a generator supply, right? Well, you have to think about how much power is going in. So, you know, a guy switching or, you know, turning a loop in a magnetic field can only power so much, right? How do you know how much power you're going to get out of this, right? There is losses and stuff like that, but basically it's whatever energy source you're using to create this electricity is going to determine how much you get out. So if you're relying on a waterfall, how much water is going through, what's the height, and stuff like that. Wind, strength of the wind, whatnot, how much heat is transferred, or how much, you know, it depends on the source. If you're having nuclear reactor, how much heat is being put out, and so on and so forth. So the power lost in the resistor is B squared L squared V squared over R. Now, what kind of power do you have to supply to get this to move at this speed? Well, remember, power is equal to from 105 F times V. So we end up with what the power that you put in, the power mechanical, okay, is equal to, and this is simply what's lost in the resistor, right? Is equal to, again, what, B squared L squared V squared over R. Okay, so this is the end of this example, and we're going to pause for a bit and continue with the next part of the discussion.